Okay, so let's start with a very quick review of what we saw in the previous class. I introduced backpropagation, and we'll see a general view of backpropagation, which is called reverse mode automatic differentiation. All right, so recall that the goal is to efficiently compute the gradient of the loss with respect to the weights. Right, and the objective function looks something like this. So this is typically what you want is to minimize the regularized empirical risk, and that boils down to finding the gradient with respect to the loss on one particular sample plus a regularization term. And the goal is to find the gradient of this particular function with respect to W. Typically, the regularizer is easy to differentiate, and you have closed form expressions for the gradient. But this is really the main challenge: finding the gradient of this loss for the L for one particular sample with respect to W. That is what requires a little more work. And the reason why we look at the specific architectures of deep neural networks is because there's an efficient algorithm to compute the gradient of such a function, because HW can be represented as a composition of a large number of simple functions. That's one of the primary reasons why these kind of architectures are particularly attractive. So we'll mainly focus on fully connected networks, where in each layer, the input or the activation to the ith layer is first multiplied with a weight matrix W, and then you apply an activation function phi I on that particular W times X. So we'll use a little bit of notation. So Zi is going to be the output of the ith layer, with the first layer having input Z0, which is equal to X. Right? And Zi is sometimes called the activation. So this is the activation in the ith layer, and phi I is called the activation function for the ith layer. So the goal is to compute the partial derivative of L of HW of X comma Y with respect to each of these weights. And as we saw, one canonical approach is to do numerical differentiation. You can just use these symmetric central differences, but unfortunately, these are computationally very intensive. Right? As we saw, the numerical differentiation requires the numerical differentiation with respect to one particular variable requires two evaluations of the function, which means that the total cost is roughly 2D times the cost of computing the function f, which is roughly like order d square, at least order d square. So the question is, can we compute the gradient using complexity, this linear in D? And as we saw, at least for the example of the single layer perceptron, it is possible to do so. And for this, we essentially just used the chain rule of differentiation, nothing more. Right? So you can write the partial derivative of L with respect to Wj as the partial derivative of L with respect to Z times the partial derivative of Z with respect to U times the partial derivative of U with respect to Wj. Right? Just to recall, the U is W transpose X and Z is phi of U. Right? Because we've represented L as a composition of simple functions, each of these partial derivatives can be evaluated easily, and the two in closed form. Right? So the loss function is something that is known beforehand. So you can write a subroutine to compute the derivative of the loss function, and so is the activation function. Right. So if we had to implement this numerically or generalize this to a larger class of functions, we could represent this as a two-step procedure. The first step is the forward pass, because in the end, you want to evaluate these derivatives at X or U z and y, right? So you first have to evaluate the point at which you want to find the derivative. So in the forward pass, you compute all of the values of the intermediate variables. That includes u and z and l. And in the backward pass, you find these partial derivatives in sequence, but in the reverse order. Starting from the output dou L by dou Z, you can evaluate dou L by dou Z at the point Z comma Y, and then compute dou Z by dou U at the point U, and then evaluate dou U by dou Wj at the point W. Right? So one can think of this partial derivative as representing some sort of an error because it's a small perturbation. And the one view of this backpropagation is that you first compute the function and then you find how much the function will perturb when you perturb wj by essentially backpropagating these errors or deviations. All right. So how would we generalize this to a two-layer fully connected network? We saw that briefly, at least not even if not completely in the last class. So we have HW of X to be phi2 of W2 transpose of phi1 of W1X. And our goal is to compute the partial derivative uh, of L of HW of X with respect to the elements in W2 as well as the elements in W1. And I guess in the last class we did it by hand. We tried to compute each of the partial derivatives. But let's look at it in a slightly more general fashion. So anyway, the first step will be to compute the values of each of these intermediate functions. So we'll use some notation for W1 times X, which is U1, and Z1 is phi1 of U1, and U2 is W2 times Z1, and Z2 is phi2 of U2, and which is our final estimate. And L, capital L, is the loss function evaluated on Z2 and Y. All right. So the backward pass to compute the derivatives, the first step is, of course, to find the partial derivative of L with respect to the last step. So maybe it will help to represent this in a diagram. So remember that we had W1, which is given multiplied with X to give you Q1, and you apply the activation function phi1 to get Z1. Now Z1 is multiplied with W2 to get U2, and then you apply phi2 to get Z2, and then you apply L to get capital L. Right? So this is a graph representation of how we are applying these various operations, and which illustrates the dependence of L on the different variables. Right? I've drawn this in a specific manner for a reason. So here you can view this as a directed graph. Right? It's a directed graph. It's acyclic. And the arrows move from the independent variables via the dependent variables up to the finally to give the function that we want to evaluate. Right? So in this case, there are two independent variables or two sets of independent variables, W1 and W2. And then you apply these various transformations or various operations in order to get the final function N. Right? So The first step, to let's say we want to find the partial derivative of L with respect to WU, or with respect to W2, then basically this is equal to the partial derivative of L with respect to Z2, or the elements of Z2, times the partial derivative of Z2 with respect to U2, and so on. That's how you would propagate, right? So let's write delta 2 to be the partial derivative of L with respect to U2. In this case, U2 is a variable, it's not a vector. Uh, so this is just equal to the partial derivative of L with respect to Z2 times the partial derivative of Z2 with respect to U2, which is the partial derivative, which is the derivative of L evaluated at Z2 comma Y times the derivative of phi2 evaluated at U2. Right? Is this okay? Great. So the partial derivative of L with respect to every element in W2 depends on, so now we've evaluated the partial derivative of L with respect to U2. So this is equal to the partial derivative of L with respect to U2 times the partial derivative of U2 with respect to W2. Right? So we get this as the partial derivative of L with respect to U2 times the partial derivative of U2 with respect to W2. And here, remember that U2 is W2 transpose Z1. So the partial derivative of, let me be a little more precise over here, because I'm finding partial derivatives with respect to individual elements. Let's write this out explicitly. So let's focus on this particular step here, right? I've found the partial derivative of L with respect to U2 to L by dou U2, which, let me just call this U2 bar. I'm using a compact notation because U2, this underlying U2 bar is a vector, and this partial derivative with respect to a vector is just a compact representation for dou L by dou U2 of 1 up to dou L by dou U2 of whatever the dimension of U2 is. Right? And I have U2. Yeah, I'm sorry. This in this particular case, U2 is just a single variable, so I don't need the vector representation. But in general, whenever I say partial derivative of some function with respect to a vector, it will essentially mean this vector of partial derivatives. Okay. So maybe I will just change this to W2 bar, which is this particular quantity. So this is the notation that I will follow. And so far we have, let's say that we have computed U2 bar, which is the partial derivative of L with respect to U2. Right? And U2 is equal to W2 transpose Z1. So the partial derivative of L with respect to W2 of I is equal to the partial derivative of L with respect to U2 times the partial derivative of U2 of I with respect to, I'm sorry, partial derivative of U2 with respect to W2 of I. Right? Which is just U2 bar, which I've computed in the previous step, times the partial derivative of U2 with respect to W2 of I. But the partial derivative of U2 with respect to W2 of I is simply Z1 of I. Right? So in this compact representation, the partial derivative of L with respect to the vector W is equal to U2 bar times the vector Z1. Any questions? Okay. So the notation here is a little bit different. It's delta 2. So it's delta 2 times Z1 or U2 bar times Z1. Now, similarly, in this case, I've found all of the partial derivatives. I've found Z2 bar, U2 bar, W2 bar. Now, Z1 bar is essentially identical. Z1 bar is just U2 bar times W2. Right? Do you agree with me? Because essentially this function is symmetric in W2 and Z1. And U1 bar, can you tell me what U1 bar should be? So I have Z1 bar, which is the partial derivative of L with respect to Z1. So this would simply be, so W Z1 bar, or if I have to write it in U1 bar of I is the partial derivative of L with respect to U1 of I. This is equal to the partial derivative of Z1 of I with respect to U1 of I times the partial derivative of L with respect to Z1 of I. And that's because the mapping from U1 to Z1 is element-wise. So this is equal to Z1 bar times phi1 prime of U1. So U1 bar, the vector U1 bar, can be written as Z1, vector Z1 bar, element-wise multiplication with phi1 prime of U1. Questions? Again, so essentially all we're doing is looking at it step by step. You have U1 and apply an element-wise mapping phi1 to get Z1. Okay, now let's go to the last step. W, you multiply with X to get U1. And W bar is the part, it's now a matrix, right? So this is, we want to find the partial derivative of L with respect to every element in the matrix W. So let's look at the partial derivative with respect to one of the elements. Should be W1. W1 of, let's say, ij. So here you have to be a little more careful because it's not this is not an element-wise operation. Every element of Z1, every element of U1 depends on multiple elements of W1. In particular, W1 ij influences multiple elements of U1. Which elements of U, so how does it depend on the elements of U1? Correct. So dou L by dou Ui dou Ui by W1 ij. Correct. Yeah, sorry. I was mixing it up with something else, but yeah, this is all that is. Right. So this is just U. Sorry, U1I. This should be U1I. So this is U1 I bar times, what is this equal to? W. Well, what's the partial derivative of U1I with respect to W1ij? X xj, right? So if you had to represent this in a succinct form, what is partial derivative of L with respect to the matrix W? Can you represent that in terms of the vectors or some vector operations on U1 bar and X? Sorry, you're close, but it's not U1 bar transpose. U1 bar transpose X will give you a number, right? This quantity over here, W1 bar, should be a matrix. No, you're just guessing. So what is the ijth element of W1 bar equal to? It's equal to this quantity, right? Yeah, correct. So W1 bar is equal to U1 bar times X transpose. right? So it's the outer product of u1 and extra of u1 bar and x. Right? Now, the advantage of a fully connected neural network is that essentially it's the same kind of operations being performed in every layer. So it's the same set of operations that happen at every single layer. Yeah, question? I mean, here, I didn't hear. Okay. We need to, because this is just a number, right? So Z1 is a vector. And only the ith element of Z1, correct. So Z1 is just phi1 of U1, right? And this phi1 is applied element wise on U1. So only the ith element of Z1 depends on the ith element of U1. Yes. Okay, I didn't quite understand. So you have U1, so this is U1 of 1 up to say U1 of D1. And on each you apply phi1, on each element you apply phi1 to get Z1 1 up to Z1 D. The ith index of Z1 depends only on the ith index of U1. No. Phi1, so that's why phi1 is applied element wise. So on each coordinate you apply phi1. Right? So the representation we are using is, so phi1 of U1, right? This is U1 is a vector. So phi1 of U1 is also a vector, and this is equal to phi1 of U1 1, phi1 of U1 2 up to phi1 of U1 D. So it's slightly abuse of notation because I'm using this phi1 and this phi1 to represent the same thing, but I could have called this something different, but it just complicates notation. That's all. So whenever there's an activation function operating on a vector, it is, so an activation function is typically a scalar valued function. So it takes a scalar as input, a scalar as output. When I'm applying it to a vector, I'm basically applying it to every coordinate of that vector. That's it. Okay. Any other questions? Okay, great. So for a general fully connected network, it's basically the same thing. So if we go back to what we did in every step here, so starting from the end, we were propagating backwards up to the sources, or starting from here, we went from L to Z2, so Z2 bar and then U2 bar, W2 bar, Z1 bar, U1 bar, and W1 bar. That's the order of computation of the bar or the partial derivatives. And each U2, or let's say at any point here, let's say u2 bar was equal to the partial derivative of z2 with respect to u2 times z2 bar. That was happening in every step, right? And that's all there is, right? There are only a few types of operations that occur in fully connected neural networks. So in a fully connected network, what you can have is some w times x, where w is the variable with respect to which you want to find the partial derivative. Or let me not use this. So I have something like wi zi minus 1, right? So I may be interested in finding the partial derivative of L with respect to Wi, or the partial derivative of L with respect to Zi minus 1. Right? So if I have U equal to W times Z, then Z bar I claim is equal to just W transpose times U bar, and W bar is equal to U bar times Z transpose. Now, we've essentially seen the calculations for this in the two-layer case, but I'll leave this as an exercise. Okay, so what you just have to show is that the partial derivative of L or whatever function L with respect to Z of I is equal to the partial is equal to um, the ith row of W transpose, or basically the ith column of W, in a product with the partial derivatives or the Jacobian of U, right? And similarly, if we have an element-wise, the only other type of operation that occurs in a fully connected neural network is Z equal to phi of U. And in this case, sorry, this should be U bar is equal to the derivative of phi evaluated at the vector U, element-wise multiplied with Z bar. Okay, so these are the only two types of operations that are going to occur. So to find all of the gradients, we only need to do these kinds of vector Jacobian products. So at every step, you find the Jacobian and you multiply it with the vector, which is what you had computed for the next layer. Any questions? Right. So basically, the step would be you first compute the forward pass amounts to computing the values of each of the intermediate variables, and the backward pass just amounts to computing each of these uh, partial derivatives. Right? Okay. So this approach is not restricted to only fully connected networks or neural networks. You can use this particular approach to compute partial derivatives of any function. Right? So if we give you a general function or a program, you can represent that function using a computation graph, which is just a directed acyclic graph with a bunch of nodes, and you get each node by performing some sort of elementary operation on some of its parents. So let's say that I have f of x1 or f of w1, w2 is equal to, say, w1 plus w2 plus sine of W1, W2. All right. Now I can represent this using a computation graph. So let me introduce some variables. Let's say that V1 is equal to W1, V2 is equal to W2, V3 is equal to W1 times W2, which is V1 times V2. V4 is equal to, say, V1 plus, or let's say V4 is sine of V3. V5 is, say, W1 plus W2, which is V1 plus V2. And V6 is V, I'm sorry? I'm sorry. Let me just do it step by step. I could just say this is V1 plus V2 plus V4, but let's say V6 is V5 plus V4. Okay. So the graph would look something like this. So I have W1, I have W2. There are two variables, and I have V1, V2, and V3 is V1 times V2. And V4 is sine of V3, so it depends only on V3. And V5 is V1 plus V2. And V6 is V5 plus V4, which is the function I want to evaluate. All right. So now again, I have a directed acyclic graph, and I can basically use the same idea to find the partial derivatives of f with respect to W1 and W2. Right. So you find the partial derivative of f with respect to V6, and I can find each of these individual partial derivatives of V6 with respect to V5, V4 with respect to V3, V3 with respect to V1, V3 with respect to V2, and so on. So the idea is still the same. There are you run through this W1 and W2, you evaluate the corresponding values of V1, V2, V3, V5, V4, V5, V6, and so on. And then find the partial derivatives, evaluate the partial derivatives by computing V6 bar, V4 bar, V5 bar, V3 bar, V2 bar, V1 bar. And that gives you the partial derivatives of f with respect to W1 and W2. Right? So I leave it to you as an exercise to do this explicitly by hand for this function. Okay, and then I mean this is a simple enough function, so you can compute the partial derivatives of f with respect to W1 and W2 explicitly. So use this backpropagation type approach to compute the partial derivative, to find V1 bar and V2 bar, and verify that it's equal to the partial derivatives of f with respect to V1 and with respect to W1 and W2. All right. So that's the general idea. So given any general function, you first construct this computation graph. All right. Where you have a bunch of nodes, and each node can be obtained using some elementary operations on its parents. And the inputs to this directed acyclic graph are the variables with respect to which you want to find the partial derivatives. And the output, so basically the child, is going to be the function that you want to evaluate. there could be multiple outputs also. So you may want to find the partial derivative of each output with respect to each input. And then you just use the chain rule in this particular manner, right? So, so this is what is called reverse mode automatic differentiation. And the general idea is that you run through this computation graph in two sweeps or two passes. There's a forward sweep or forward pass where you evaluate the values of each of these intermediate variables in the order going from the inputs to the outputs. And then there's a reverse sweep or a reverse pass where you compute the so-called adjoints. So you run from the output to the input in the reverse order, and you evaluate each of these partial derivatives. So for any variable u bar, for any variable u, any intermediate variable u, let's say I have u being connected to v1, v2, or say vi1, vi2 up to vij, u bar, which is the partial derivative of f with respect to u, is simply equal to summation overall I1, I2, I3, and so on. So it's equal to the partial derivative of f with respect to vi1 times the partial derivative of vi1 with respect to u plus the partial derivative of f with respect to vi2 times the partial derivative of vi2 with respect to u, and so on. So there's nothing fancy going on here. It's just plain old chain rule, but applied in a careful and clever manner. That's it. That is all there is to automatic differentiation and backpropagation. But it has to be done a little carefully. But there are just one or two very simple rules that need to be followed. Yeah. Yes.
There is a node,
Huh.
and that is a variable z. If you only care about rho L by rho Z,
Correct.
then multiply with rho Z by rho U. Right?
Correct.
Why are we here adding multiple paths?
What do you mean multiple
Like
paths?
here you showed an example, right? U depends on multiple paths.
You mean this? No. So in this case, it's the reverse. So these nodes, all of these depend on the variable u. So in this, even in this previous example here, right? So here v5, both v3 and v5 depend on v2, and similarly, both v3 and v5 depend on v1. That happens in neural networks also, but then we had this very succinct form, and that's why you didn't see the. So let's take a very maybe that's what I was coming to get at. Basically, suppose this variable feeds into multiple or has multiple children, right? Which is what I depicted in this particular picture. It happens in a fully connected network whenever you have these inner products, right? And in general, that will happen. Even this toy example that I took here, you have this vertex having two children, right? And the claim is that u bar is simply equal to sum over all possible children of the child bar, the partial derivative of the function with respect to that particular child node, times the partial derivative of that child node with respect to u. Right? It's just the same, right? So you have, say, G. Let's take this. Correct. So it's just u, which depends on, say, C1 and C2, say, and you have this final function f, There could be multiple nodes in between, but I can just represent that compactly. So f is some function of C1 and C2. Let's say this is, let me represent this using G. All right. So I want to find f of u, which is, say, some G of C1, C2, where C1 is some function of u and C2 is some function of u. That's the situation that I'm in, right? So if I use the chain rule, what is it equal to? What is dou f by dou u equal to? It is dou g by dou C1 times dou C1 by dou u plus dou g by dou C2 times dou C2 by dou u, right? And that's all that is being represented here, nothing else. Okay, and we'll this particular fan out in the sense how many children does a particular node have will also determine the computational complexity of doing backpropagation and many other things. And we'll revisit this when we get into convolutional neural networks and ResNets. Okay. So one other thing to keep in mind is that I call this reverse mode automatic differentiation. There's also a notion of a forward mode automatic differentiation. Now remember that whenever we were doing this backpropagation or this automatic differentiation, what we were essentially doing is we had this computation graph. And what did the computation graph store? At each node, we computed the value of the function and the partial derivative of that particular, or the partial derivative of f with respect to that particular node. Right. So given a node, right, node v, we computed the value of v and v bar, which is the partial derivative of the function that we want to compute with respect to v. So these are the two things that each node has to eventually compute. And this is called reverse mode automatic differentiation because this v bar, what we were trying to compute, was the partial derivative of the final output with respect to each of these variables. Now, you could also do this in the so-called forward mode, wherein you compute the partial derivative at each node. You find the partial derivative of that node with respect to the input. So dou v divided by dou, say, wi, where wi is one particular input. Okay, so let's say I have a sequence of nodes. Say I have w and a final function f. In reverse mode, what you basically did was found the partial derivative of this node with respect to f, and then this node with respect to f, and then this node with respect to f, and so on until you reached the partial derivative of f with respect to, I'm sorry, the other way around. So let me call this v1, v2, v3, v4. In reverse mode automatic differentiation, you found the partial derivative of f with respect to v4, and then partial derivative of f with respect to v3, then with respect to v2, and then with respect to v1. Right? That was the approach that we followed. Now, another way of doing this is, again, using the chain rule itself. You could first find the partial derivative of v1 with respect to w, and then again, using the chain rule, you could find the partial derivative of v2 with respect to w, which is the partial derivative of v1 with respect to w times the partial derivative of v2 with respect to v1. And then you find the partial derivative of v3 with respect to w, and so on. So instead of finding the partial derivatives in this reverse order, you could also do it in the forward order. Right? They're both valid approaches to build the computation graph and compute these derivatives. But then in terms of complexity, both of these have different computation complexities. So the forward mode if you have a general function from Rd to say Rk, then the forward mode would require d sweeps of this computation graph, because in every sweep you are finding the partial derivative with respect to one of the variables, right? And there are d variables, d input variables, but then you get the partial derivatives for all of the outputs with respect to that one particular input. If you did reverse mode automatic differentiation, then you need k sweeps, that is the number of output variables. But typically in machine learning, these loss functions that we're interested in, they take as input a large number of variables. So D is very, very large, which is the number of trainable parameters. And we want to minimize just one loss function, which is a single, which is a real valued function. So, so here D is very large, whereas K is equal to 1. So it makes more sense to use reverse mode automatic differentiation, which is just the backpropagation algorithm. Right? Any questions? So the complexity of forward mode automatic differentiation is just D times the number of nodes in the graph, essentially. And reverse mode, it is K times the number of nodes in the graph. Right. So the reverse, so one thing to, so this was all at a very high level about automatic differentiation and backpropagation, but there are some implementational aspects to also be kept in mind. One thing that you would have noted is that this reverse mode must store all of these forward activations, uh, and then compute each of these gradients, right? You don't need to store all of the partial derivatives, because the partial derivative for one layer only depends on the partial derivatives for the next layer. And it really doesn't depend on the partial derivatives of all layers ahead of that particular point. You can just get rid of that, just to save memory. But then you need you need to be able to store all of the values, which is the activations. So if you have a very deep neural network, then the total memory that is required will grow with this depth. And that can be a huge bottleneck. Because typically what you do is you store all of these. So all of these computations typically happen on either your RAM or typically a GPU. And the memory that is available on the GPU is limited because it also has to store a lot of things, including these intermediate variables. Right. So sometimes what people do is you do what is called checkpointing. You don't store all of the forward activations. You store only some of them, maybe roughly, if there are m layers in your neural network, then you only store roughly root m of those. And then when you do the back propagation, you recompute all of the intermediate values. So that the total amount of memory that is required is now much significantly lower. Right? And this is extremely important because today we have like very large neural networks which don't even fit on a single GPU. So everything you can do to save memory and save computation will be equally valuable. Which ones? You typically do it at a regular interval. So let's say you don't recompute, or you don't store the first root m. So only after root m layers you store, and then for the next root m layers you don't store, and so on. That's what is typically done. But then there are a lot of other engineering optimizations that one does. There are other approaches. For example, let's say I have multiple GPUs. Then what I can potentially do is sort of split the model into two parts, and then store some in one GPU, some in the other. But that leads to a host of other challenges as to how these two GPUs must talk to each other during the backward pass and so on.
So here we are not taking any importance of the subgradients.
No, no, no. All of them are assumed to be equally important.
Cannot be take the importance.
What do you? How do you choose which? How do you decide which ones are important?
So some neurons have some high values. Like we can take the receptor field of the particular neuron and try to find what are neurons are affected.
But it gets a lot more complicated, right? Because so this is what you have to store are the forward pass activations, right? And to find so let's say you have one neuron which is in, say, the first layer. If I want to find the partial derivative of the function with respect to some neuron in the first layer, then I need all of the intermediate values stored in all of the layers in front ahead of that, right? That's what we're trying to save on, right? Because if you find the gradient with respect to that particular neuron, which may be the important neuron that you're interested in, you should look at all of the neurons that at least this neuron influences, correct? Which that becomes an optimization in itself, which could potentially be much harder. There are other approaches, there are other kinds of optimizations you can use, because in the end all of this depends on how well you construct this computation graph. There could be ways of simplifying the computation graph to reduce complexity somewhat, and that's also a difference between how you implement Autodiff in practice. Uh, what you could do is, given a function, complicated function, you first try to construct the entire computation graph, and then maybe optimize over it. Maybe you can prune some nodes, or as you said, decide if, let's say that you want to find the partial derivatives only with respect to certain neurons, then you could get rid of all of the other uh, variables or intermediate nodes that don't get influenced, and thereby reduce computation. But so that was what was done in early variants of TensorFlow. But today, typically, you do it very dynamically. For example, what PyTorch does is, as and when you do a particular computation that's part of the forward pass, it just stores it. Right? So every time you say multiply two variables, and you say that you will need it for automatic differentiation, then it adds that node, or adds a new node to the computation graph, and builds the computation graph as and when you do the computations. There are advantages and disadvantages of both. Um, one, there are also many advantages for dynamic graphs, particularly when you do things like recurrent neural networks and so on, where it's very difficult to represent that using a static graph, or the graph itself has to vary or changes at runtime. Let's say you have the number of operations put in some loop, right? And depending on how many loops this goes through, the graph itself could become bigger and bigger. Right? So all of those with such complicated settings, it's difficult to work with static graphs. So dynamic graphs are typically used in PyTorch, and I believe also in TensorFlow today. All right. So in essence, what PyTorch is a library that allows you to perform operations on tensors. Automatic differentiation is one primary such operation, but there are a lot of other built-in operations that you can do. Also, coming back to your earlier question about what do you do when the functions are non-differentiable, you use a subgradient instead of the actual partial derivative itself. And generally, whenever you have ReLU activation functions, you typically take 0 as the subgradient by convention, although there are multiple subgradients. There are infinitely many subgradients at 0. And when there are discrete operations, for example, you have quantized values. Let's say the There are certain variables that are assumed to be discrete. They don't take a continuous range of values. Then there are other tricks that one can play, and one such approach is this technique called the straight through estimator, wherein in the forward pass you evaluate it exactly, but in the reverse pass, because it's discrete and it's not differentiable at any point, and therefore you can't even find a subgradient, you approximate it by some other function. So it's a hack that you try to play. And all of these approaches can be used even to find higher order partial derivatives. So for example, you could do what is called double backpropagation to find the Hessian of a particular of a function with respect to whatever variables you have. All right. So basically, you now have to build a computation graph for the gradient, and then once you computed the gradient, you do another backprop. Okay. So one thing to keep in mind is that automatic differentiation, which is basically the workhorse of PyTorch, TensorFlow, and similar libraries, is firstly, it's different from numerical differentiation, as we saw, because automatic differentiation or backpropagation allows you to find the derivatives in time that is linear in the number of variables. But it's also different from what is called symbolic differentiation. There are other libraries or packages that try to interpret the symbols themselves, because the symbolic differentiation, you assume that there's a template of functions and they use something similar to the chain rule to find the partial derivative or derivatives of these more complicated functions constructed from simple functions. So in the end, what automatic differentiation does is that it allows you to find it allows you to express partial derivatives of complicated functions using partial derivatives of simple functions, right? Now, how do you find the individual partial derivatives? That varies, because in the end, to find each of these, right? Let's say to find each of these values, you have to find either, if you have a closed form expressions for such partial derivatives, then it's fine. But at times you don't have closed form expressions for such things, in which case you will have to do some form of numerical differentiation to evaluate these. Okay, so you can use numerical differentiation within automatic differentiation also. What, for example, PyTorch does is that for certain simple kinds of operations, like functions like sine or log or exponentiation, it also has built-in functions, or under the hood, it computes the partial derivatives for those functions exactly. Right? Any questions? Okay. So with this, we'll move to the next topic. So just to summarize what we did so far. So initially, we sort of built a recipe for training any machine learning model given a supervised learning problem, right? And for a generic supervised learning problem, what we saw that effectively what we should do is do regularized empirical risk minimization. Right? That's what we want to run. And in addition, maybe you do some kind of model selection or cross-validation, things of that sort. And how do you do the regularized empirical risk minimization? It's difficult to do it exactly in practice. So you replace that with a gradient descent or stochastic gradient descent type of algorithm. And now with automatic differentiation and backpropagation, at least for, say, fully connected neural networks, we have a complete recipe. We know how to find the gradients efficiently. And having found the gradients efficiently, we can run stochastic gradient descent and therefore train We know how to do end-to-end training of any fully connected neural network or any feed-forward neural network in general. Right? As long as you can build this computation graph, you can find the gradient, and once you find the gradient, you can run stochastic gradient descent. So let's now spend a little bit of time on one specific supervised learning problem, which is classification, and see some of the other intricacies that arise within classification itself. Right? So just to recall, what was the classification problem? We're given a feature space X and a label space Y, where the number of labels or the number of classes is assumed to be finite. It could be 2, which is binary classification, or it could be more than 2, which is multi-class classification. And when we are talking about the learning theoretic formulation, we assume that at any point we're observing samples x comma y, where x and y are jointly distributed according to pxy, where pxy is unknown. Right? We'll use a little more terminology. So we'll refer to py as the prior class probabilities and px given y as the class conditional densities or the class conditional probabilities. Okay. So in principle, x and y are just being jointly generated at once, but we'll view this in the following setting where we assume that first you pick a particular class at random, and given this particular class, you generate a sample from this class according to px given y. Okay? It's one particular view of generating the sample x comma y. And we are doing all of this to understand how to choose our hypothesis class. So far, given a hypothesis class, for example, a fully connected neural network, we know what to do. We know how to train a neural network, or at least do uh, empirical risk minimization, or regularized empirical risk minimization using stochastic gradient descent. But how should we choose the hypothesis class itself? Or even when doing empirical risk minimization, we need to do it over some particular loss function. Right? If you recall, if in classification, we want to do empirical risk minimization with respect to the 0-1 loss. But the 0-1 loss is not differentiable, it's not convex. So a lot of things break down. And we want to approximate the 0-1 loss using some other loss function. So what choice of loss functions are okay for classification, and why are they okay? That's what we want to address in the next in this particular discussion. All right. So again, in the context of classification, we saw that the Bayes optimal decision rule is just to choose for a given x, you choose that particular y which is most likely. So this essentially just corresponds to the maximum likelihood decision rule. So if we knew the joint distribution, or if we knew py given x, then the optimal choice of the predictor would be this, the Bayes optimal decision rule. Right? And when we are trying to choose our loss functions and also choose our predictors using neural networks or whatever approach, we want to draw intuition from the Bayes optimal rule itself. Is it possible to sort of mimic the Bayes optimal rule in some way by imposing some assumptions on what we know about the problem? Okay, that's going to be the general approach. And for the Bayes optimal decision rule, the risk, which is the 0-1 risk or the probability of error, is equal to this particular quantity. How do you justify? How do you prove that this is actually the Bayes risk? So given a particular x, this is what the Bayes optimal rule outputs. All right. So given a particular x, conditioned on x, what is the probability of error? So let's assume that y can take three different values, 0, 1, and 2. And for a given x, for one particular choice of x, maybe you have p0 given x to be equal to, I don't know, 0.1, p1 given x to be equal to 0.7, and p2 given x to be equal to 0.2. Okay, so py1 given y equal to 0 given x is 0.1, py equal to 1 given x is 0.7, and py equal to 2 given x is 0.2. Now, having observed this particular x, what does the Bayes optimal rule output? It outputs 1, because that is the one with the highest probability. And when are you in error? When either y is equal to 0 or y equal to 2. So what is the probability of that happening? Yeah, so it's probability of 0 given x plus probability of 2 given x, or equivalently 1 minus the probability of 1 given x. So this is equal to 1 minus max overall y, py given x equal to little x of y, right? And so the Bayes risk is simply the expectation of this particular quantity, which is just the integral over all x of this times px dx. All right. Any questions? Correct.
So should we be the probability of y actually consider
Yes.
super if we take ML estimate of this?
Correct.
Which is saying that it's probably that ML estimate doesn't give zero,
Correct.
but then there may be some cases that ML estimate gave one, but actually y was
Correct. So suppose that the ML estimator outputs 1 in this case, right? If the true value of y is equal to 1, then there's no error, right? So the 0, 1 loss that you incur is 0. You incur a loss of 1 if y is either equal to 0 or it's equal to 2. But what is the probability of that event happening?
shouldn't be like something like 1 minus sigma y not equal to 1 probability of y.
Correct.
But here we are saying
No. So it's not the prior, right? It is conditioned on this event that x is equal to little x. Because what is the predictor seeing? The predictor is seeing this, right? So conditioned on this, I mean, so this is the probability of error given that x is equal to little x. So the overall probability of error is the probability is basically the expectation of this particular quantity, which is again the integral over x of this times the probability of x dx. Did that answer your question?
so that
Sure. Right. Any other questions? Okay. So now, given this particular background, let's forget neural networks for now. How do we design a particular classifier? So the sort of intuitive approach that we want to use is we want to do something that kind of mimics the Bayes optimal rule, right? And there are two different ways of doing this. One is sort of a generative approach, where you model the prior and the class conditionals as coming from some class of distributions and try to fit the distribution depending on the data that you see. All right, that's called the generative approach. And then having fit this particular data, you again do the Bayes optimal rule for that class of distributions. You just use Bayes theorem to evaluate the probability of y given x. The other approach is the so-called discriminative approach, wherein your model itself tries to approximate py given x. Right? So in the end, our problem with designing a predictor directly is, suppose that what is our goal? Our goal is to design a predictor which, given a particular x, outputs a class, right? One of discretely many classes, finitely many classes. And if we try to design a model for that does this, it's very difficult to optimize because the number of outputs is finite. So I can't run stochastic gradient descent. I don't have a continuous function from the inputs to the output, because the inputs is some continuous valued variables, but the output is finitely many and therefore not continuous. My goal is to reframe this problem in a way where the inputs and the outputs are both continuous and I have a smooth function linking the two. So the question is, can we design a model which outputs py given x? Instead of outputting an estimate for y, can it just output an estimate of py given x? If it does so, then I know the Bayes optimal rule is to choose that y with the maximum py given x. Okay? So again, there are two different approaches. In the generative approach, we try to estimate or approximate px given y and py separately, and then use the Bayes rule in order to choose the best output. All right. So in general, these generative models will require a lot more assumptions and are not so common these days. It's the discriminative models that we'll primarily look at. So, but nevertheless, we'll look at some classical generative classifiers, the what are called linear discriminant analysis and quadratic discriminant analysis, wherein you model each class as being Gaussian, right? So the assumption is that y can take essentially corresponds to one of multiple means and covariance matrices, mu y and sigma y, and given a particular y, the features px or the features x are drawn from a Gaussian distributed with mean mu y and covariance matrix sigma y. Right. So the goal is therefore to maximize log. So effectively, maximizing py given x amounts to maximizing px given y equal to y times py of y. Right, so that's the maximum a posteriori probability rule. Right, so and you can sort of simplify this to show that this what you want to maximize is this particular quantity. And depending on how you encode the assumptions on mu y and sigma y. So the goal, therefore, is given the data, you want to estimate this mu y and sigma y. Okay. And once you've estimated or approximated mu y and sigma y for the different values of y, you plug that into Bayes rule, and given a particular input x, you find that y which maximizes this particular quantity. So in general, if you assume that sigma can depend on y, then you get a decision boundary that looks like a quadratic function. But then if you assume that only the means, the mu depends on y, then the corresponding boundaries turn out to be linear. And here's an exercise: show that the corresponding posterior is equal to, just can be represented as this perceptron. Show that if you want to maximize this particular quantity, or if you assume that px given y is distributed as follows, and you try to find the posterior, then the boundary is linear. That is the decision rule for choosing y equal to 0 or y equal to 1 turns out to be to have a linear boundary, and py given x of say 1 given x is exactly equal to sigma of w transpose x plus b, where w is given by this particular quantity. This also gives you some additional information. So it's easier to distinguish between mu1 and mu0 if these two are sufficiently far apart. If mu1 and mu0 are far apart, and it's harder to do so if they're not. So essentially what LDA is trying to do is approximate the class conditional densities as Gaussians, so that all it amounts to is choosing the right decision rule for two different Gaussians. All right. And if you also assume, if you encode additional assumptions, for example, that the covariance matrix sigma is also diagonal, then you get what is called naive Bayes classifier. All right. So now you could use a completely different approach, which is you use logistic regression to approximate, to directly get py given x. So if you did logistic regression for the same problem, then it's essentially the same thing, right? You're trying to represent py given x as sigma of w transpose x plus b, which is a discriminative approach, whereas LDA is a generative approach. The difference between LDA versus logistic regression is how you represent w. In logistic regression, you're trying to learn w directly from the data. In LDA, what you're trying to do is W has this very specific form of sigma inverse mu1 minus mu0, and you're trying to learn sigma mu1 and mu0. All right. So you're trying to learn these and try to plug in mu1, mu0, and sigma into this particular quantity. All right. So logistic regression is basically where you take the output of your so-called predictor is just sigma of w transpose x or sigma of w transpose x plus b, where sigma of u is just 1 by 1 plus e to the minus, right? And your decision rule, your final decision rule is going to be hw of x is just, you choose either the one with the highest value of beta, or you could also play around with the value of beta. So you set a threshold and you declare 1 if, again, this is for binary classification. The you do first do logistic regression, which outputs a probability of y being equal to 0 or 1 given x, and you set a threshold. If this probability or estimated probability is greater than tau, then you declare 1. If it is less than tau, then you declare 0. Right? There's a specific reason why I want to choose a tau rather than just half. Now, choosing either 0 or 1, depending on whether P0 given X is higher or P1 given X is higher. That just amounts to indicator beta of X greater than or equal to half. Right? That's what you would do. But here I'm deliberately choosing a threshold tau which could potentially be different from half. Okay, and we'll see in the next class why I may want to choose a tau which is different from a half. Okay, any questions? Previous? Yes. You mean this one? Or? Correct. This is assuming you have a generative model.
Try to find the line or some value after that. If it is greater than that, it will be plus.
Correct. Yes.
So a VP common people is how generative and discriminative models are.
So basically, in the generative model, you're trying to fit distributions for Py and Px given y. Two different distributions. Effectively, you want to build a model that tries to estimate Px given y and estimate Py. On the other hand, in the so-called discriminative model, you directly try to estimate Py given x. So this is called the generative model because it's like you first generate y, and given y, you generate x. So that's just the difference in terminology. In the end, you need a discriminator in both cases.
We don't need the distribution for generative clearly.
We do. So the assumption is, again, it depends on how you approximate Py and Px given y. One way to do so is you assume that these class conditionals are Gaussians. So the only free parameters left for you to choose from are the mean and the variance or the covariance. So you use the data to learn the mean and learn the covariance. Now the actual data generating distribution could be different. It need not be a Gaussian, but you're trying to fit a Gaussian nevertheless. But that's an optimization problem that is efficient to perform. It's computationally not very intensive. And that is why you go for these approximations.
Basically, we assume that Px given y will follow some distribution.
Correct. So this comes from this sets the hypothesis class.
We will try to understand the parameters which will define
Correct.
instead of finding which class.
Correct. Because once you fit the parameters, everything else is fixed. Because once the parameters are fixed, you just use Bayes optimal. That's it.
But in discrimination,
you directly get Py given x. So, for example, this cannot be Gaussian anymore because the number of choices of y is limited. It's finite, right? Any other questions? Okay, so let's stop here.